All right, so this is another classic problem that you need to be able to work through. We have a sheet of metal, a rectangular sheet of metal is 8 by 10 inches. Now I don't have metal, I have a sheet of paper here. And so let's suppose this is 8 by 10 inches. And we're going to cut a square from each of the corners. So to draw a picture of that, we're going to have a rectangular sheet, and from each of the corners, a square, the same size square, is going to be cut. Right? And so we have, that's what's happening here. I'm going to cut square from each of these corners. And then when you cut that square out from each corner, so I'm actually doing that process here. Cut the square from each of those corners. All right, we generate something like this. And then you fold the edges up. And if you seal those seams within the limits of my very quickly and hastily and not very accurately cut paper, you can construct a box in 3 dimensions. All right, see my box? So the question is, how big should that square be so that the box you make has the maximum possible volume? Now, if the square you cut, see what we're going to do is take this and we're going to fold those edges up. And make a box, right? Well, if the square you cut is very, very small from each corner, that can be done. But now do you see what's going to happen? These edges that you flip up are going to be very thin, and so what you're going to generate is something like this. In fact, it's going to look like a cookie sheet that you would use to make cookies in the oven, right? And the volume that encloses is very small. Now, as the edges, as the squares get larger and larger and larger, then this gets thinner and thinner in the box. And now the question is, what is the largest possible square? If this is 8 inches from here to here, what is the largest possible square you can cut from both corners? If this is 10 inches from here to here, what's the largest possible square? Well, is it clear? You cannot cut 8 and 8, because once you cut 8 from here, there's nothing left to cut. You could cut 3 inches from both, that's allowed. You could cut 3.5 inches from both, that's allowed. But is it clear? When you cut 4 from here and 4 from here, you've run out. There is no box present anymore. Now, a person might say, well, what about the 5 and the 5? Well, you get to 4 on this side before you get to the 5 on this side. So the moral of the story is this: the largest possible square, if I'm going to let x be the side of this square that I'm cutting out, the largest possible value of x, the largest possible value for x is half the shorter side. The largest possible value for x is half the shorter side. In this case, the largest possible value for x is 4. The smallest, theoretically, you could cut no square at all. The smallest possible value for x, theoretically, is 0. The largest possible value for x, in this case, is half the smaller side, is 4. So when we form this function here pretty soon, we know going in that the interval over which x is defined is from 0 to 4. Any critical value we get in that interval we use, any critical value we get outside that interval we don't use, and potentially the maximum value could come from one of the endpoints. And we'll do the specifics of this problem in the next video.